Welcome back to the Tech Talk podcast. Today we're diving into the intriguing world of database storage engines, specifically focusing on two key structures, log-structured merge trees or LSM trees and B trees. Whether you're a developer, a data enthusiast, or just curious about how databases operate behind the scenes, this episode will clarify how these systems efficiently manage data. So grab your headphones and let's get started. Let's kick things off with LSM trees. When a write operation occurs, the data is first stored in an in-memory structure called a memtable, which acts like a balance tree. Imagine a red-black tree. This memtable organizes key value pairs in a sorted manner. Once it fills up, typically reaching a few megabytes, it gets flushed to disk as an SS table, or sorted string table. This process is efficient because the data is already sorted, making it straightforward to write to disk. Meanwhile, new writes can continue to be added to a fresh memtable, keeping the system responsive. When it comes to reading data, the system first checks the memtable for the requested key. If it's not found there, it moves on to the most recent SS table on disk, then to older segments until it locates the key or exhausts all segments. To maintain performance, a background process merges and compacts these segment files, discarding outdated or deleted entries. However, there's a catch. If the database crashes, any recent writes still in the memtable would be lost. To address this risk, a write-ahead log is maintained on disk, where every write is immediately appended. Although this log isn't sorted, that's perfectly fine. Its primary purpose is to restore the memtable in case of a crash. Once the memtable is safely written to an SS table, the corresponding log entries can be discarded. This approach underpins popular storage engines like LevelDB and RocksDB, which are embedded in various applications. The concepts were inspired by Google's Bigtable paper, which introduced terms like SS table and memtable. The original idea of LSM trees came from Patrick O'Neill and his colleagues, and it has proven effective, especially for managing large datasets that exceed available memory. Now let's switch gears and talk about B trees, a structure that's been around since the 1970s and remains widely used today. Unlike LSM trees, B trees manage data in fixed-size blocks or pages, typically around 4 kilobytes. This design aligns well with how GISCs operate, as they read and write data in fixed-size blocks. In a B tree, data is organized hierarchically. Each page contains several keys and pointers to child pages that represent continuous ranges of keys. When searching for a key, you start at the root page and follow the pointers down through the tree until you reach the leaf page containing the actual data. This structure allows for efficient lookups and range queries. Inserting a new key is a straightforward process. You find the appropriate page for the key and add it there. If there's not enough space, that page splits into 2, and the parent page is updated to reflect this change, keeping the tree balanced and efficient. However, deleting keys is a bit more complex, since it requires maintaining that balance. One of the main differences between B trees and LSM trees is how they handle data modifications. B trees can overwrite existing pages directly, which can be risky if a crash occurs during the operation. To prevent corruption, B trees often use a write-ahead log, ensuring that all modifications are logged before being applied to the tree structure. This way, if a crash happens, the B tree can be restored to a consistent state using the log. Concurrency control is another crucial aspect of B trees. When multiple threads access the tree simultaneously, it's essential to ensure they don't encounter an inconsistent state. This is typically managed using lightweight locks or latches. In contrast, LSM trees handle concurrent writes more easily since they perform merging in the background without blocking ongoing queries. Over the years, various optimizations have been developed for B trees. For example, some databases use a copy-on-write strategy instead of directly overwriting pages, which helps with concurrency control. Others focus on packing more keys into pages to increase efficiency and reduce the number of levels in the tree, speeding up lookups. Another optimization involves the layout of pages on disk. While B trees can become fragmented over time, some implementations strive to keep leaf pages in sequential order on disk to minimize disk seeks during range queries. This can be challenging as the tree grows, but it's crucial for performance. LSM trees, on the other hand, can more easily maintain sequential order during their merging processes. Lastly, there are B-tree variants like fractal trees that incorporate some ideas from log-structured approaches to reduce disk seeks and enhance performance. These adaptations illustrate how flexible and resilient the B-tree structure can be, even as technology evolves. So there you have it. We've explored the inner workings of two powerful data structures, LSM trees and B trees. Each has its strengths and weaknesses, making them suitable for different use cases. LSM trees shine in write-heavy scenarios and can efficiently manage large data sets, while B trees deliver robust performance for read-heavy operations and maintain a balanced structure. Understanding these storage engines is vital for anyone working with databases, as they form the foundation of how data is stored, retrieved, and managed. Whether you're developing an application or optimizing an existing system, knowing when to use LSM trees versus B trees can make all the difference. Thanks for tuning in to this episode of the Tech Talk podcast. If you enjoyed the discussion, be sure to subscribe for more insights into the world of technology. Until next time, keep exploring and learning.